Why isn't the universe behaving as expected? Imagine setting out to solve one of the biggest mysteries in physics, like a detective piecing together the clues to uncover the truth about the cosmos itself. Welcome, curious explorers, to this journey into the enigmatic universe, where nothing is quite as it seems, and every answer leads to new questions. Today, we dive into one of the biggest puzzles in modern cosmology, the so-called Hubble tension, a perplexing issue that's left scientists scratching their heads. This mystery deepened with a discovery made by none other than the James Webb Space Telescope, which captured a strange supernova that appears 3 times in a single image. The problem with the universe's expansion rate: for years, scientists thought they had a solid understanding of the universe's expansion rate. This Hubble constant, named after astronomer Edwin Hubble, is supposed to give us the rate at which galaxies are moving apart due to the Big Bang. Yet, measurements tell a strange story. When scientists predict the expansion rate based on observations of the early universe, they get one value. But when they measure it using nearby stars and galaxies, the numbers don't add up. So, what's causing this discrepancy? And how does it shake our understanding of the universe? The two methods of measuring the expansion: we're about to dive into 2 very different ways of measuring this expansion rate, both of which are crucial to understanding the universe. The first method, based on the Standard Model of Cosmology, combines theories with observations from the cosmic microwave background. This radiation is a relic from about 380,000 years after the Big Bang and fills the universe to this day. Through this method, scientists calculate the Hubble constant to be around 67 km per second per megaparsec, meaning that for every 3.26 million light-years, the speed at which galaxies move apart increases by 67 km per second. But when scientists use the second method, which relies on observing specific objects like Type Ia supernovae and Cepheid variable stars, celestial objects with predictable brightness changes, they get a different number, around 73 km per second per megaparsec. That's a 20,000 km per hour difference in the cosmic speed limit. The cosmic detective, James Webb Space Telescope, with the Hubble Space Telescope unable to fully solve this tension, scientists turn to a new tool, the James Webb Space Telescope, our cosmic detective. Imagine a lens so powerful that it can peer into the farthest reaches of space, into galaxies formed only a few 100 million years after the Big Bang. Webb's infrared sensors and spectrographs allow it to analyze faint light sources, giving us unprecedented insights. Recently, Webb spotted something unexpected: a supernova that appeared 3 times in a single image. This wasn't a glitch, it's an effect known as gravitational lensing, where light bends around massive objects like galaxies. This phenomenon turned out to be more than a visual curiosity, it's a potential new tool to tackle the Hubble tension. Gravitational lensing and the supernova called SN Hope. This supernova, nicknamed SN Hope, is unique because of its gravitational lensing properties. Scientists discovered 3 images of the supernova due to the lensing effect of a massive galaxy cluster. Each image is like a time lapse of the same explosion, showing different moments in the supernova's life. Why is this important? Because gravitational lensing provides an unprecedented way to measure distances and, ultimately, the Hubble constant. By studying the lensing effect, scientists can get a precise look at the universe's expansion rate, but this raises even more questions. When a constant isn't constant, how can the Hubble constant vary so much? If it truly is a constant, shouldn't it apply uniformly across the universe? These findings have left scientists reevaluating what they know. Could it be that our models are incomplete? Perhaps there are unknown particles or forces at play, or maybe the nature of dark energy, the mysterious force driving the universe's expansion, is more complex than we thought. One possible explanation is that the universe isn't as homogeneous as we assumed. Imagine the universe as a fabric with different densities and regions where expansion behaves uniquely. Or could it be that we're missing something fundamental about time and space? SN Hope, a new hope in cosmology. This isn't just a discovery, it's an experiment unfolding in real time. The SN Hope supernova provides 3 snapshots of the same cosmic event, viewed from different angles and moments in time. Each image represents a data point that can help refine our understanding of the Hubble constant. Scientists have now taken this triple-lensed supernova data and applied it to the Hubble tension. They measured the constant to be about 75.4 km per second per megaparsec, a number that fits better with recent observations but doesn't fully match predictions from the early universe. This tells us that while the SN Hope findings are groundbreaking, they deepen the mystery instead of solving it outright. Could our cosmic models be wrong? Astrophysicist Adam Rees, a Nobel laureate, suggests that our current understanding of the universe might be incomplete. There could be new types of particles or fields, entirely unknown forces, or exotic forms of dark matter influencing the expansion rate. What if the universe is a layered structure, with each layer following its own expansion rules? Dark matter and dark energy, the unseen puppeteers. This discrepancy might involve dark matter and dark energy, 2 mysterious substances that make up about 95% of the universe's mass-energy content. Dark matter acts as an invisible glue, while dark energy pushes galaxies apart. But what if dark energy varies over time and space, or if there are forms of dark matter we haven't discovered yet? Imagine if we found that dark matter isn't just a passive force but interacts in ways we can't yet see, influencing gravitational lensing and altering how we observe the expansion. Such a discovery could fundamentally change our understanding of physics. Future observations and the road ahead. Webb isn't finished yet. The telescope will continue to search for other gravitationally lensed supernovae and more standard candles to test the Hubble constant further. These observations could give us the final pieces of the puzzle, or they might reveal new questions we never thought to ask. So, curious explorers, what are we to make of this Hubble tension? Are we on the brink of a new era in cosmology? Or does this discrepancy suggest we've been looking at the universe all wrong? Let's leave you with a question: do you think the universe is playing tricks on us, or are we simply looking at it through the wrong lens? Could there be civilizations out there watching us, struggling with their own cosmic mysteries? Thank you for joining us on this deep dive into the Hubble tension. If you enjoyed this journey and want more explorations of the cosmos, make sure to hit the subscribe button and click the bell icon so you never miss a video.